Shell sort, or also known as Shell's method, is an optimization of insertion sort that allows elements to be moved over large distances in the early stages of sorting. Before we formally discuss shell sort, we need to revisit the insertion sort algorithm. Let us say we have the numbers 6, 5, 4, 3, 2, and 1. In an insertion sort algorithm, we identify a key, which is the number you want to check and place in the correct position. In this example, 5 will be our first key. We check, is 5 greater than the number before it? No, so 5 shifts to the left. Now, our key is 4. Is 4 greater than 6? No, so 4 shifts to the left. Is 4 greater than 5? No, so 4 shifts to the left again. This process repeats until every number has been placed in its correct position. This process is straightforward, but it creates a problem. What if we had more numbers? Insertion sort checks one step at a time, which becomes very slow on large or heavily unsorted lists. Let us now discuss shell sort. Shell sort improves on insertion sort by first comparing elements that are far apart, then gradually reducing the distance between comparisons. This allows elements to travel large distances quickly in the early iterations. By the time we are comparing neighbors, the list is already nearly sorted and very little work remains. The key concept in shell sort is the gap, which is the distance between elements being compared. Shell sort starts with a large gap, followed by a round of comparisons. Then the gap shrinks and repeats. It continues until the gap reaches 1, at which point it behaves exactly like an insertion sort. This is why we say shell sort is an optimization of insertion sort. The best case scenario is that the gap-based early iterations already sort most of the list. But in the worst case, the gap sequences fail to pre-sort the list effectively, making it no better than a plain insertion sort. This detail will be discussed more in the efficiency analysis. Now, let us look at the Python implementation of a simple shell sort algorithm. We will walk through this using the list 20, 15, 10, and 5. Always remember that in a list, the index starts at 0. With this, at index 0, our value is equal to 20. The code for the shell sort algorithm has 3 loops: an outer while loop, a for loop, and an inner while loop. But first, let's go line by line. This defines our function. It takes one argument, list val, which is the list of numbers we want to sort. In our example, that is 20, 15, 10, and 5. This computes our initial gap, or the distance between elements we are going to compare. We start by floor dividing the length of the list by 2, which roughly places our first comparisons at the midpoint of the list. You may notice this uses a double slash rather than a single slash. The double slash is called floor division, and it divides and then discards any decimal values, giving us a whole number. This is essential because the gap will be used as an index later, and list indices must be whole numbers. In our example, the list has 4 elements, so gap is equal to. This is the outer loop. It keeps the entire sorting process running. After each full pass through the list, the gap gets halved. This loop keeps on repeating until the gap eventually reaches 0, at which point everything has been sorted. You might ask, why 0? This is because a gap of 0 is not a meaningful gap value. It would mean we will be comparing an element with itself. This for loop moves through the list during each pass. It starts at the gap value rather than at index 0. The reason is that we need to look gap positions behind the current element to find something to compare against. If we start at index 0, there will be nothing gap positions before it and we would go out of bounds. Although negative indices exist in Python, this occurrence will cause the algorithm to check the opposite side of the list, which we do not want. In our first round, with the gap equal to 2, the for loop runs for index 2, then index 3. This saves the value at the current index or the element we are trying to place in the correct position. In the insertion sort analogy, this is the key. We save it separately because in the next steps, we will start overwriting positions in the list. If we did not save, we would lose the value we are trying to insert. At index 2, our list is 20, 15, 10, and 5, so our current value is 10. This creates a second tracking variable that will move backwards through the list as we search for where current value belongs. It starts at the same position as the index, so at first, inner index is also equal to 2. To summarize, current value remembers the actual number we are inserting, and inner index tracks where we currently are as we move backwards. You might ask, why are we moving backwards? This is because we do not want to compare any number we have not processed yet. Searching backwards ensures that every element that is bigger than the current value gets shifted forward by gap position. This is the inner while loop, or the heart of the algorithm. It has two conditions that must be true for the loop to continue. First condition is that it asks if there is a valid element gap positions behind. If inner index is less than the gap, we will be looking at a negative index, which would cause the algorithm to compare elements from the opposite side. Condition 2 asks, is the element that is gap positions behind bigger than the value I'm trying to insert? If yes, the bigger element needs to shift forward. To properly visualize this scenario, here is an example. Again, we have a list input of 20, 15, 10, and 5. It is indexed from 0 to 3. Reading the code, it asks if the inner index is greater than or equal than the gap, which is true. Next, we need to solve for the difference of the inner index and the gap. This results to 0. However, 0 just represents the index for the list value. At index 0, it is equal to 20. Next, it checks if 20 is greater than the current value of 10, which is true. If both conditions are satisfied, we shift the bigger element forward by gap positions, overwriting the current position. However, remember that this is not a swap. We do not move current value. We simply shift the bigger element forward. We do not swap because swapping would require 3 variables per shift. For example, it will require temp, A is equal to B, and P is equal to temp. This approach only requires one operation per shift, and then one final placement. So this method is more efficient. Instead of doing multiple swaps, we just shift bigger elements forward and drop current value into the gap left behind at the end. Next, we move our pointer back by exactly gap steps to check the next number behind. Why exactly gap steps and not one step? Because in shell sort, we are working within a gap size domain. All elements in this pass are spaced gap positions apart. Moving back by gap steps means we stay within the correct group and compare the right elements. Stepping back by any other amount would mix up elements from different groups. In this example, our inner index is now 0, failing the condition 1 of the while loop. Once the inner while loop requirements are not satisfied, either because we hit the boundary or found an element that is not bigger than the key, we place current value in the slot at inner index. This line serves two purposes. If the inner while loop ran at least once, it fills the empty slot created by shifting. If the inner while loop never ran at all, it means the element was already in the right position, and it simply writes the value back to its original position, leaving things unchanged. Since the for loop is only at index 2, it still has one more index to go through. If we repeat the process we did earlier, our list will now look like this. At the end of our inner while loop and for loop, after the for loop completes a full pass through the list, the gap gets halved. This gradually narrows the comparisons, bringing the algorithm closer to a standard insertion sort with each round. When the gap reaches 0, the outer while loop ends and the sorting is complete. Let us now have a step-by-step walkthrough of the algorithm. On our previous line-by-line explanation, we have already performed one iteration of the while loop. This is now how our list looks like. Let us continue this example. With a gap equal to 1, since we halved our previous gap, the algorithm now behaves like an insertion sort. The for loop runs for index 1, 2, and 3. Our current index is equal to 1, making our current value equal to 5, and inner index equal to 1. Continuing to the inner while loop, we satisfy condition 1, meaning we are still within bounds. We also satisfy condition 2, 10 is greater than 5. 10 now moves to the position of 5, and inner index gets reduced to 0. Since inner index no longer qualifies for the first condition, the while loop is not triggered. 5 now gets saved into its correct slot. Our index is now 2. making our index and inner index equal to 2. Our current value is 20. Checking the conditions for the inner while loop, we pass condition 1. However, condition 2 is not satisfied, as 10 is not larger than 20. With this, we skip the while loop completely, implying that we are already at the correct position. We now overwrite the value of 10. Moving on to our final iteration for the for loop, our index and inner index are equal to 3, making our current value equal to 15. Checking the inner while loop, we fulfill condition 1 and fulfill condition 2. 20 overrides the position of 15, and we reduce the inner index value by 1, making it equal to 2. We check the conditions for the inner while loop again and satisfy the first condition. However, we fail at the second condition, breaking us from the inner while loop. We save the correct position of 15 and finish the for loop. Since the for loop is finished, the gap is once again halved. However, since the quotient is equal to 0, the outer while loop ends, leaving us with this sorted list. Unlike many sorting algorithms, shell sort does not have a fixed time complexity. Its performance depends heavily on the gap sequence used. This is what makes shell sort different and complicated. In a worst-case scenario, the time complexity is big O of n squared. The worst case occurs when the gap sequence is poorly suited to the data. With the simple floor divide by 2 gap sequence, a reverse sorted list exposes this weakness. This is because elements from different gap groups are never really meaningfully compared until the final pass at gap equal to 1. By this point, the list is still largely unsorted, causing the inner while loop to trigger for nearly every element in the final pass. As mentioned, the gap sequence can be poorly chosen because it can be changed depending on the type of list you have. In this example, we used the originally proposed gap sequence. To further explain the time complexity, it all boils down to the 3 loops. First, the outer while loop runs log of n times. Why? Let us say we have a list containing 6 elements. Each iteration of the outer while loop, the gap gets halved. This sequence of halvings is approximately log of n iterations. However, for this gap sequence, it is log base 2 of n. But why base 2? This is because we are dividing by 2 each time, meaning the base directly depends on the gap sequence. In this case, it moves in a log base 2 manner. Next, the for loop will run n times. Lastly, the inner while loop will also run n times in the worst case, because it must shift almost every element. Combining all 3, the worst case time complexity becomes big O of n squared. The average case has a time complexity of big O of n times log squared times n. The average case applies to randomly arranged lists. Since the data is random, the inner while loop triggers not all the time but some of the times. The main difference lies in the inner while loop partially triggering across iterations. Because previous gap phases have already partially sorted the list, each element only needs to shift a logarithmic number of times on average. This results in a time complexity of big O of n log squared 10. Always remember that time complexity differs per gap sequence. The best case is big O of n log n. The best case occurs when the list is already sorted or nearly sorted. In this situation, the inner while loop rarely triggers, so shifting hardly occurs. The outer while loop does not change. It will always remain the same. The same can be said for the for loop. It will iterate depending on the length of the list. The main difference lies in the inner while loop. Since the list is almost or fully sorted, the condition is rarely satisfied, meaning it will rarely trigger, making the best case time complexity of big O n log n. Let's go with the pros first. First, fast on partially sorted or medium-sized lists. The gap-based iterations means elements move large distances in early iterations. This reaches the correct index quickly. By the time the gap reaches 1, little work remains which the insertion sort struggles on. Next, it is fairly simple to implement. The shell sort is simple. It is just an optimized version of an insertion sort. Moreover, it is straightforward to understand and write, making it practical to use. Next is very flexible. With its flexible gap sequences, the shell sort algorithm can be catered to the nature of the list. Let us now go to the consequences. First is very inconsistent in terms of time complexity. However, the inconsistent time complexity, it depends on the list and gap sequence used. This unpredictability makes it harder for the sorting method to be used on real-life scenarios. Next, worst case is no better than the insertion sort, making it inefficient. Lastly, the gap sequence tuning is non-trivial. While flexibility is a strength, it also means getting the best out of the shell sort requires research and testing. The simple gap sequence that was used earlier is very easy, but not optimal. Implementing a better sequence adds complexity to a simple algorithm. Shell sort is relatively smart insertion sort if the gap sequence is well chosen, and the list is partially sorted. However, given the wrong conditions, the shell sort offers no advantage over the insertion sort algorithm. Ultimately, the shell sort algorithm is one of a kind. Its flexibility and capability to cater to your data makes it unique. In practice, its performance ultimately depends on how well its gap sequence aligns with the structure of the data being sorted, making it a very situational tool. Thank you!